And we've asked Professor Martin to outline some best practice in sustainable district heating and storage solutions. Professor Martin, I'll hand over to you now and ask if you wouldn't mind sharing your screen and walking us through your presentation. Thanks again for joining us today.
Okay, thank you. I will go ahead and stop my video because I'm going to tilt my screen here when I hope to also scribble some things to clarify. So I trust that you can hear me and also see the screen as long as nobody says anything else.
We can, thank you.
I just need to minimize you as a group. There. Okay, so I thought the title I was asked to elaborate on was very intriguing. If there are any innovations in district heating and energy storage. So just a little bit of my background. I will not linger here. I am professor then in energy technology over at the KTH, which is the Royal Institute of Technology in Sweden. It's our largest engineering university, you can say. And my area of research, as briefly mentioned, if we look at technologies, I work a lot with thermal energy storage and also heat-driven heat pumping technology. And here I get a good use of my now sort of old background, where I have a Master of Science from KTH in chemical engineering, followed by a PhD in mechanical engineering way back in '98 from the University of Florida. So anyway, related to systems, I work with large interest on district energy systems and work with industrial energy systems as well, and looking at applications, how we can also make them decentralized energy generation and services, also for developing regions of the world. And I include my shorter form of email address, so I would like you to please send me feedback on this lecture, and if you have any questions, don't hesitate to contact me. It would be good if you refer to this course then, so that I sort of know the context of you all. So I know from Harpreet that we had gotten, you had been given some background reading, and for just when they share the slides, I also attached the links here to the different cases. So for the Herlin district heating network, that is just to give us a set point from where I continue my talk today. There you read about a circular district heating system which used groundwater filled mines for heating and cooling of buildings. And in this context, you could then say that this groundwater was heated by geothermal energy by the flowing through the surrounding ground of the mines. When a building in this context then was cooled, it releases heat to the cold carrier in that case, and that is returned to the mining well and stored as heat. In the other direction, when the building is heated, we bring warmer water from the mine or heat from the mine well, and then it returns colder, and thus we charge this store with cold. For this, we need to have this heat pump technology to make sure that we deliver the right temperature to the buildings to service their demands. So very simple schematic of the heat pump, because it's going to be present in a lot of the discussions today. But basically you use a low-grade heat source, for example, water from this mine well, or it could be wastewater streams or things like that. You take 2/3 of that and combine it with 1/3 of mechanical work input, electricity driven often, and produce the heat at the correct temperature. In this way, you can really use the system to also absorb surplus electricity from wind and PV station as heat in an efficient way via the heat pump. And this is what they have been working with here as well. The interesting thing to point out, I think, is that here the concept is really just working with established technologies. So nothing really new in here. It's just how you link it all together in a smart way. You have water, you have a water field mines, you have your demand side, and you have heat pump. And there you go. Your Kalundborg case is an industrial symbiosis, and here by sharing or integrating a number of actors or different types of demands with regards to water, energy, and material flows, you optimize the system and try to find elements of circularity in there so that surplus energy from one industry can be used to heat another building, for example. And the objective in that project was to minimize the outflows from the symbiosis project. And your last reading that I was informed of was the Hamburg case. And here, of course, they set out to get rid of the coal out of their district heating systems and replace it by biomass and waste incineration and also solar heat. They're looking into a couple of storage solutions like transforming an air raid bunker into a heat reservoir and even pumping hot salt far into the ground. So we can talk about that later. But the emphasis in that article was, of course, that here the municipality bought back the utility and claimed that not only, I mean, you have innovative ideas, but they felt that a municipality-owned situation could get further or dare to do more in this context. So I'm not saying whether that's true or not, but just one sort of social implication that I believe you should always consider when you look at projects. Coming from that then, I would like this very short lecture to bring you some confidence in the area, but my third bullet point here, I want to enable you to explore relevant resources by yourself and also be able to discuss among yourselves and other colleagues the implications of, for example, how storage can aid in making district heating based on renewable resources. So with this said, what is district heating? It is mostly as simple as boiling some water. So not a very high-tech idea, perhaps. But when we discuss district heating, it can mean so many things. This image is from the Your Heat and Power website. Really, where how the water is heated can come from so many sources, and of course it can be a coal-fired boiler or combining heat and power with coal as a basis. But what we're aiming for is to look at ideas on how can we bring cost-efficient and resource-efficient solar thermal, make use of waste to energy or biomass and so on into the district heating concept. There, and then we can look at this evolvement presented by the initiative on the 4th generation of district heating. You have the website here, but I also give you other links. And we can look how it has evolved over time. So if we start back at the early 1900s, we have the first generation of district heating, which was primarily steam-based, and it was very local. You didn't bring the heat so far by steam. High temperature then with the steam, and also the return temperature coming back after delivering the heat was rather high, and efficiency was so-so in that scenario. Then moving into between the 30s and 80s, large-scale generation presented as the second generation district heating was presented, and here we moved from steam to actually delivering the heat in hot water systems that were pressurized so that we could go slightly over 100 degrees during the coldest hours of the day. Still, the return temperature had quite a high value in this case. And also we can see that we get the heat storage, and that was perhaps more due to economy reasons than sustainability reasons, but working with combined heat and power coal and coal waste as the basis. Then we move towards where we are today, the 3G. We have gotten a lot of knowledge on how the pipes can be pre-insulated. They need to be insulated. We are delivering hot water still below 100 degrees most of the times, except for the coldest hours of the day. We have done much better at lowering the temperature of the return to about 45 degrees. And what does that mean in lowering the return? That means that per cubic meter, for example, of water that we pump in the system, we have delivered more energy. So that's why it's an aim to have a low return temperature. We have some elements of renewables in this mix already. There are some large-scale solar installations, and for example, in Sweden, most of our district heating is based on biomass, wood chips, etc. Combined heat and power is linked to this, so we co-generate electricity and heat and deliver it as hot water. Then we have some industrial surplus in many cases, refineries and things like that, steel mills, aluminum foundries and things. And some backup still exist with coal and oil as the basis. So for the future then, the innovation goes towards the 4th generation, and this project here has been ongoing for several years. What it's looking at is to have low temperature, 50 to 60 degrees water delivered, or something called even ultra low district heating in this context, which is when the water delivered is 30 degrees C. And we want to have the return coming back here from around 25 degrees. What that means is that we will be able to harvest, for example, surplus heat from data centers is something that is highlighted. And other types of waste heat streams in society could be linked if we work with the lower temperatures. And still working with getting the renewables in here, absorbing surplus electricity and make it into heat via heat pumps, for example, work with heat storage and so on. So this has been very hyped. Now things are starting to, so you see here the target area or the target year is 2050, but things are starting to roll quite rapidly. And then we move into the 5th generation of district heating, which is starting to co-develop in parallel. This is still in early stage of development. You have the main difference between 4th and 5th generation is that you put in the same pipes provide heating and cooling. And I will give an example of that. You let the temperature in the piping system float, and you also keep the temperature very close to the ground. I mean, 30 degrees, 20 degrees, and so on, to minimize heat losses. And I will provide you a link later with the, for example, you can check out the FlexiNet project for many examples of where this is ongoing. Smart is also in here. You use data analytics and ICT solutions to make the network operation in a smart way. Okay, but back to basis. This is a schematic of a system in the city of Växjö in Sweden, a city that was awarded some years ago some European prizes because it's CO2 neutral already. It lies in the countryside with a lot of forest, so it can make use of wood residue and so on to carry the district heating. And it's a combined heat and power block, and they service buildings with hot water, and also through the heat they use a absorption chiller to also provide cooling to the hospital. So they are co-generating heat and cold and power at the same time. Fundamental when you move into these new types of fluids are to integrate the flue gas condensation. And what that is doing is it takes from the boiler the flue gas and cool it with the district heating return in this box here. You cool the flue gas below the dew point so the water comes out and it gets drier, and in this way you preheat the incoming water from the district heating return line. So this is and it can be a substantial part of the overall heat addition in the plant comes from this flue gas. Another thing, Swedish example with this more wet type of fuel or complicated fuel is an investment done 2014 in the city of Västerås. They commissioned a 167 megawatt circularized fluidized bed boiler. So here it's not so much innovation in the layout of the district heating plant itself as it is an innovation in how you pre-treat the fuel. So you can use all kinds of fractions. So here they co-fire biomass, but also municipal waste, which is pre-prepared, crushed. You have a magnet pulling out metal, and then the fractions that are heavy, like rocks and glass and stuff, are sorted out and deposited in a good way before you move the fuel to the incineration. And they use it in a combined heat and power plant. Last thing before we move into storage, so I'm running out of time, is a concept ETCOgrid that I wanted to raise because it's similar to the Herlin case of the water-filled mines that you have studied. So I say it's nothing new under the sun, but they have managed to trademark the concept, speaking of innovation. And they put it forward as time to start sharing for sustainable cities. So what it is all about is one of these 5th generation district heating systems that use the same network for heat and cold. And it has heat pumps between each building and the grid. So a building make deposits and withdrawals of heat and cold to this one circular system. And your accumulative demand of all buildings have to be balanced. So hopefully you have connected demands that have cooling and heating at the same time. Otherwise, we see that it will not work. So energy is only added to the grid when needed. they want to optimize the sharing. Here again, you do not have so much new technologies as you have the whole setup of innovation is in the business model, how you use ICT and so on to manage this system. Okay, so closer look at the energy storage. I will move a little faster here. Basically, we have the sun. So I claim, and you can study my figures I had before I moved on here, energy is not a problem. We have 3 times as much solar energy intercepted on Earth, 3 orders of magnitudes higher than what our annual global demand is. So the problem is a mismatch in time, place, and temperature. So of course, time is where storage come in. We have energy when we don't need it, so we need to storage to shift. And for the storage, many times the discussions go towards batteries. But in a recent webinar from the International Solar Energy Society, it was stated that over 80% of demand for heating and cooling and transport. So it's beyond actually storing electrical power opportunities. And renewables are lagging behind in the heating and cooling sector, actually. So with that said, you can store in many ways. What I will look at today is primarily when you store thermal energy of heat and cold. And here you can talk about storing it in different ways: sensible, latent, and thermochemical. And sensible storage is basically the state of the art. Hot water accumulators, where you use thermocline, you make use of the water's density difference. So the warmer water is floating on top, and the colder water is at the bottom. And you, as long as you keep that thermocline steady, you have a good storage capacity in a hot water accumulator. And this image of a real one here is a 40,000 cubic meter water storage from this city of Växjö with a biomass CHP. And that's only enough to manage the peak hour demands in the mornings when people take showers on a cold winter day. So they charge up this with hot water and use it in the morning. But if you need to store larger volumes for more days, seasonal or monthly, the best option is really to go underground. And for example, you can then do it in a tank that you bury underground. Here is a steel tank, or a pit, which is different from a tank in that you have the ground itself as the barrier, as the shield. You don't have a steel tank. Or you put boreholes so that you actually, and this we have to the right here an image, you actually pump down hot water in the ground and then you heat up basically the ground. And it's a double tube coaxial heat exchanger here, which you run the heat carrier. And here mostly you have charged it lower heat, like 30 degrees at the maximum. But now there are cases coming where you actually charge up the ground to up to 60 degrees. And then you store the heat underground during the summer. When you put in this thermal energy storage test, you enable the use of industrial surplus heat for societal use and also absorbing surplus from wind and power, because you have this mismatch in time. Distance, of course, and temperature sometimes, but the storage makes, for example, a main industrial process, which could be a batch style process. It makes it able to deliver to building demands which may not match the available heat. You can think of other clustered industries making use of a steel industry, for example. You place a commercial greenhouse or laundry facility close by, it could run off of the steel mill surplus. Here is an example of seasonal storage for solar heat from Drake Landing community in Canada. And you can understand why they need seasonal storage. They have sun during the summer and hardly not so much sun in the winter when there is a heat demand. So what they do is then they charge the borehole store with the seasonal storage. They have a hybrid concept, so they also use water tanks to for the daily storage, so they can charge and discharge the storage in the ground at a lower pace compared to the actual fluctuation in power demand of the community. Merging concepts here, you see a lot. For example, there was a PhD thesis from DTU presented not so long ago, which made use of this phase change material. What phase change material does is that you have a salt or paraffin or something melting at, for example, 60 degrees. So you have this solid, you provide heat, and then it melts and becomes a liquid. And this can give you a storage capacity of up to 100 kilowatt hour per cubic meter. And you can compare that to just heating up water and using it 90 to 45 degrees. That gives you storage capacity of 50 kilowatt hour per cubic meter. So if you want a compact store, using phase change materials could be a really good option. And the concept that they had is to charge seasonally heat in PCM bank here, and then use the water tank for the daily demand leverage in a combination. What I want you to think about and contemplate is the cost of such an investment compared to the ground, for example, because you invest in a salt, which could be cheap, but still to seasonally store in the ground would be cheaper still. So although it's a nice idea, think also of other aspects. What I want to say is that this phase change material, which I do work with a lot, that serves another purpose when we cannot use water at temperatures higher than what water is capable of, and also when the ground is not an option, such as boreholes and aquifers and so on. A concept that we have worked on, for example, is when we cannot have pipe transferred heat because the distance is too far between a steel mill here in one city. You can melt the phase change material and then basically transfer the heat as molten salt to Stockholm area, where we don't have this industrial surplus. So heat on wheels is such a concept. You put it on a boat or you put it on a truck and integrate it into a system where you have the demand. Coming to the end, going over time, which I promised not to do. Some concluding remarks to you. And I realize this is a very short whirlwind of cases, but anyway, there are many commercial and pilot plants showing the 4th generation district heating concepts. So you can go out and explore them, and also some 5th generation concepts, which has to do with using this same piping for cooling and heating. And in this 5th generation, they treat district heating and cooling together, but also match temperature levels to actual demands. So we need to heat our homes at 20 degrees C. We don't use 90 degrees C water to do it. And this enables also multiple sources to be used and minimize heat losses in the system. So storage of heat and cold, which is then thermal energy storage, is important, a good addition to battery technologies when you look at resource and cost efficient solutions. And we can also use it to absorb fluctuating wind and PV as heat in such systems. But what I want to stress is that the local conditions are always very, very important to how you set up your successful projects. So you need to include the particular business landscape and policies that are present, and of course other local conditions like that. So with that, I would like to thank you for your attention and leave you with some links to additional reading. And I can now open up